Okay, dear colleagues, let us start our today BIM's Integrable System seminar. And today our speaker is Jirui Guo from Tonzi University about Bethe-Grothendieck polynomials and quantum integrable systems.
Good afternoon. And I would like to thank the organizers of this seminar for giving me this opportunity to present my recent work. This work is on an integrable system construction for the quantum cohomology and the quantum K-theory of flag varieties, which also encodes the double Bethe-Grothendieck polynomials. I will start with a review of the quantum cohomology and the quantum K-theory of flag varieties and the double Bethe-Grothendieck polynomials. And I will also review the integrable model in the Grassmannian case studied by Gorbunov and Korf. And then I will present you the GLN asymmetric 5-vertex model that is Bethe equations and how it encodes the ring relations of the quantum cohomology and the quantum K-theory ring of flag varieties. And finally, I will talk about its relationship with the double Bethe-Grothendieck polynomials. So first, as you all know, the flag variety consists of flags, which are sequences of subspaces inside a given vector space with the dimensions specified by a sequence of increasing integers. Here I denote these integers by AI. And there are topological bundles on this variety with the fiber of so here SI are the topological bundles where the former one is a subbundle of a latter one, and the fiber of SI at a given flag, say V, and the fiber of SI at this flag V is VI, the I subspace of this flag. And there are subvarieties inside the flag variety, which are called Schubert varieties. They're indexed by permutations in Sn, the group of permutations of n elements with descents in this set consisting of the integers ai. And given this W and fixed complete flag, say F, the Schubert variety omega WF is defined by specifying by imposing requirements on the dimension of intersections of VI and FPs. And the codimension of the Schubert variety indexed by W is the length of W, which is the minimum number of simple transpositions used to express the permutation. Okay, then if we denote this omega AW, denote by omega AW the cohomology class corresponding to the Schubert variety indexed by W under Poincare duality, then these Schubert classes form a basis of the cohomology ring of the flag variety. And these cohomology rings can be presented in terms of polynomials, the polynomial ring and some relations. For example, in the case of complete flag variety, the cohomology has this presentation where the relations are given by the elementary symmetric polynomials in variables. In this presentation, the variables xi's can be identified with the classes of the quotient bundles SI mod SI minus 1. And the Schubert class omega W is represented by the Schubert polynomial, which is denoted by XW here. And for general A, this omega AW is represented by Schubert polynomials, symmetric, and in these. So first we need to, with the choice of A, we need to partition the variables into several sections, with the I section having exactly AI variables. And this XW is symmetric in the variables of every section. Okay, and in the classical cohomology, where the structure constants are nothing but the intersection numbers of the Schubert varieties. The small quantum cohomology ring is a deformation of this classical cohomology ring. It's other than the sum over the permutations, there's also a sum over the degree. The degrees are indexed by the degree 2 homology classes of the variety. Here, this notation with 3 Schubert classes in angle brackets denote the 3-point genus 0 Gromov-Wheaton invariant. Naively, it counts the number of rational curves, the number of stable maps from rational curves to the from 3-punctured sphere to the flag variety, and which has degree D, which also meets the corresponding Schubert varieties. And on the other hand, the K-theory ring of the flag variety, the Grothendieck group of the coherent sheaves of the flag variety. And the set of structure sheaves of the Schubert varieties constitute the basis of this group, of this ring. And these Schubert classes are represented by the Grothendieck polynomials. Again, given a special choice of A, these GWs are restricted to be asymmetric in the variables within every section of the partition given by A. And the quantum version is defined by the K-theoretic Gromov-Wheaton invariance. And first, we have a pairing. This pairing is defined at the bottom line, which is defined by the 2-point Gromov-Wheaton invariant. And then the product between 2 Schubert classes and another Schubert class is given by the sum over the degree and the 3-point Gromov-Wheaton invariance of that degree. Okay, so far we have talked about quantum cohomology and quantum K-theory, but on top of that, we can also add an equivariant structure by considering the torus action on Cn with weights T1 through Tn. So in this case, we can define the equivariant version of the quantum cohomology ring and the equivariant version of the quantum K-theory ring. In this case, the representatives of the Schubert classes are given by the double Schubert polynomials and the double Grothendieck polynomials, respectively. So they're not only depend on the variables x, but also on the variables the weights, which are also called the equivariant parameters. About the definition, actually, the double Schubert and double Grothendieck polynomials are special cases of one parameter family of polynomials called the double Bethe-Grothendieck polynomials, first proposed by Fomin and Krylov. And it can be defined like this. It is defined, first we need to define this beta divided difference operator, partial beta I, acting on the polynomial ring. by this formula. As you can see, if beta is 0, this is just the ordinary divided difference operator. Now assume assume this W, this permutation is the permutation in Sn with maximal length, then the corresponding double beta Grothendieck polynomial is defined by this product. And for other permutations, the corresponding polynomials can be defined recursively on the length of the permutation. So if the length of WSI is smaller than the length of W, then GWSI is defined to be GW acted by this beta divided difference operator. In particular, when beta is 0, these beta Grothendieck polynomials reduce to the Schubert polynomials, and when beta is equal to -1, these beta Grothendieck polynomials reduce to the ordinary Grothendieck polynomials. Okay, now let's talk about the integrable model corresponding to the quantum cohomology and quantum K-theory of the Grassmannians. This model was first studied by Gogolov and Korf. The R matrix of this model is given by this, where this xo minus y is defined to be x minus y divided by 1 plus beta y. And the Lax operator is defined by this, this matrix. So it's a spin chain system. And so the Hilbert space, the local Hilbert space at each side is C2. And this sigma plus and sigma minus are just the raising and lowering operators on the on the particular site. And as in general, as in the general case, the monodromy matrix is constructed by the multiplication of several Lax operators in the auxiliary space. So here LAI means that the Lax operator acts on the auxiliary space and the I spin. If we regard this monodromy matrix as a matrix in the auxiliary space, then we have the matrix entries are operators acting on the Hilbert space of the entire system, which are denoted by ABCD here. And it satisfies the RTT relation. And the transfer matrix is defined by this trace over the auxiliary space of this diagonal matrix times the TA, which is just the A plus QD. This diagonal matrix that actually imposes a twisted periodic boundary condition. Because of the RTT relation, the transfer matrices with different spectral parameters commute with each other. Okay, let V0 and V1 be the first and second unit vectors in C2, and define the pseudo vacuum to be the tensor product of n copies of V0. Then, as in the algebraic Bethe-ansatz method, we can construct the Bethe-ansatz state to be several B operators acting on the vacuum state. And this Bethe-ansatz state is a common eigenstate of the transfer matrices if these parameters x1 through xk satisfy this Bethe-ansatz equations. And one can show that if beta is equal to 0, and if we identify the ith elementary symmetry polynomial in x's with the ith Chern class of the topological bundle S, then these equations are exactly the ring relations of the equivariant cohomology of the Grassmannian GRKN. If on the other hand, if beta is -1, then if we identify the S elementary symmetric polynomial with the ith wedge product of S, then these equations are the ring relations of the equivariant quantum K-theory ring of Grassmannian. Actually, Gorbunov and Korf did more than this. They defined a Frobenius algebra structure on the Hilbert space and showed that this Frobenius algebra is isomorphic to the quantum cohomology or the quantum K-theory ring of the Grassmannian. And moreover, the expansion coefficients of the Bethe ansatz state in the spin basis of the factorial β-Grothendieck polynomials, which are double β-Grothendieck polynomials corresponding to permutations with one descent. And these polynomials can also be computed by the partition functions of the corresponding 2D lattice model. And so the natural question to ask is if we can generalize these results to the case of more general flag varieties. Actually, integrable system for quantum cohomology and quantum K-theory of the cotangent bundles of flag varieties exist, but not the flag varieties themselves. And also double β-Grothendieck polynomials can also be computed by some 2D lattice models. So inspired by these previous works, our goal is to find a quantum integral model for general flag varieties and general double β-Grothendieck polynomials. Okay, so next, let me present the model. So this is a GLN model, which means the local Hilbert space at each site is Cn. And the R matrix can be defined as follows. If we decompose the Cn as a direct sum of C and Cn minus 1, then the R matrices can be defined recursively. First, when n is equal to 2, this R matrix is taken to be the same as that for the Grassmannian case. And for n greater than 2, the R matrix can be defined in this block form, which has a repeated pattern. And the lower right block is just Rm minus 1, the R matrix for the GLN minus 1 system. So it can be shown that with this definition, the R matrix satisfies the Yang-Baxter equation. And if we, unlike Gorbunov and Korf, I take the Lex operator to be the same as the R matrix. And if we take the auxiliary space to be the direct sum of C and Cn minus 1, and as always, define the monogamy matrix to be the product of n R matrices in the auxiliary space, then it can be expressed as this matrix with the matrix. The entries of the matrix are operators acting on the Hilbert space. And the pseudo vacuum is defined to be the tensor product of n copies of the first unit vector. And from the expression of the R matrix, it can be shown that the A operator fixes this pseudo vacuum state, and the Dij operators acts on the pseudo vacuum state diagonally. Okay, and from the RTT relation, we can also get these commutation relations between A, B, C, and D, which are crucial in deriving the Bethe-ansatz equations and also in computing the expansion coefficients of the Bethe-ansatz states. And as in the Grassmannian case, we insert a diagonal matrix when constructing this transfer matrix. This diagonal matrix M imposes a twisted periodic boundary condition. And again, from the RTT relation, it can be shown that these transfer matrices with different spectral parameters commute with each other. Okay, this is the model, and let's see how the Bethe-ansatz equations are related to the quantum cohomology and the quantum K-theory ring of Vec varieties. This GLN system is integrable, meaning that it can be solved exactly by the algebraic Bethe-ansatz method. So the first step is to construct a Bethe-ansatz state, which is obtained by applying a bunch of B operators on the pseudo vacuum state. But here, because it's a GLN system, there are multiple B operators. So even if the number of B operators to apply is fixed, there are still many choices. So in general, we have to take a linear combination of all of these choices. So here, this psi1, these psi1s are the combination coefficients of all these states. And these sigma1, sigma2, and so on are parameters to be determined. Actually, these psi1s can be viewed as the expansion coefficients of the Bethe state of a GL n-1 system with K1 sites. Yeah, because we can choose these in the formula at the bottom, we can choose these ISs to take value from 1 to n-1. Originally, the state each side can take values from 0 to n-1. So here the dimension of the Hilbert space is reduced by 1. So it's a GL n-1 system. In this system, the sigma1s, sigma1, 1, sigma1, 2, and through all the way to sigma1, K1, serve as the equivariant parameters of this GL n-1 system. So you can see by this procedure, we have reduced the problem from a GLN system to a GL n-1 system. And we can keep doing like this. And at each step, we have to introduce a bunch of parameters serving as the equivariant parameters for the next step, which are also the spectral parameters in the current step, and also the equivariant parameters for the next step. And we can continue to reduce the dimension of the Hilbert space until we get a GL2 system, which is just a spin chain system as before, which can be solved exactly by ordinary means. Then we get equations from this GL2 system. We get Bethe-ansatz equations for sigma n-1. For the sigma n-1s, and we plug them back in the previous step and so on until we get a full set of equations for all these parameters. So at the end of the day, we get these Bethe ansatz equations. Sorry, there's a typo here. There should be E here. So these are the Bethe ansatz equations. So the first equation is it contains the equivariant parameters Ti, and the quantum parameters the Q's are determined by the diagonal entries of the matrix M. Remember that when we define this transform matrix, we insert a diagonal matrix M, and these BIs are the matrix entries of M, and QS is BS minus 1 divided by BS. Okay, these are the Bethe ansatz equations, and how are they related to the ring relations of the quantum cohomology and the quantum A theory? So first, let me comment from the physics point of view. So in order to relate it to the flag variety, we need to restrict to the cases in which the Kn minus 1, K2, and K1 to be increasing sequence, strictly increasing sequence. And when beta is equal to 0 or beta is equal to 1, these equations reduce to the equations for the Coulomb vector of the 2D or 3D supersymmetric gauge linear system models corresponding to the flag varieties, respectively. These gauge linear system models are gauge theories, which is quiver gauge theories, which are whose quiver diagrams look like this. So each circle is a gauge group. So a circle with Ki in the middle represents the UKI gauge group, and the square stands for the UN global symmetry, and the arrows in between represent chiral superfields in bifundamental representations. These gauge theories have the following properties. So first, the Higgs branch of the GLSM is a nonlinear supermodel with target space being the flag variety. And the chiral ring, or the operator product expansions of the A-twisted model, is exactly the equivariant quantum cohomology or the quantum K-theory ring of the flag variety in the 2D and 3D cases, respectively. And these ring relations are encoded in the equations for the Coulomb vector. So this shows that our Bethe ansatz equations indeed give rise to the ring relations of the quantum cohomology and the quantum K-theory ring from the physics point of view. From the mathematics point of view, we can derive the ring relations from the Bethe ansatz equations by using the Vieta's formula. So first, let's consider the beta equals 0 case. We can rewrite the Bethe ansatz equations in this form. So we take beta to be 0 in these equations, and then we identify Ti with sigma 0, and we take K0 to be capital N and Kn to be 0. Then those three lines can be combined to this single equation. Okay, and then if we rewrite it in terms of the symmetric polynomials, then we can see that these sigma m's are roots of this polynomial with indeterminate x, where this EI sigma s is the ith elementary symmetric polynomial in the variables sigma s's. And notice that this polynomial has degree k sub m minus 1. Then it means that there should be another k m minus 1 minus km roots. So assume the other k m minus 1 minus m roots are eta b's, eta m b's. Then the Bethe's formula use this equation at the bottom. So remember that the Bethe formula expresses the elementary symmetric polynomials in the roots of the polynomial in terms of the coefficients of the polynomial. So the left-hand side of this equation is actually just the Lth elementary symmetric polynomial in all the roots of the polynomial, and the right-hand side is determined by the coefficients. Okay, from this equation, if we identify the ith elementary symmetric polynomial in sigma m as the ith Chern class of S n minus m, and the ith elementary symmetric polynomial in eta m with S Chern class of S n minus m plus 1 mod S n minus m, then this equation at the bottom of this slide can be rewritten as this equation in terms of the total Chern class. Total Chern classes of the tautological bundles and the universal quotient bundles. And these are the quantum Winning relations of the equivariant quantum cohomology ring of the flag variety. Because this equation involves cohomology classes of different degrees, so the precise way to read this equation is to view this as a bunch of relations with both sides of the same degree. Likewise, if beta is equal to -1, and if we regard the ith elementary symmetric polynomial in 1 minus sigma m as the ith wedge product of S n minus 1, and also the ith elementary symmetric polynomial in 1 minus eta m's as the ith wedge product of S n minus n minus m plus 1 mod S n minus m, then this equation down here can be rewritten in terms of the lambda y classes in the Grothendieck group like this. So this lambda y class is defined by the formula at the bottom. So it's a sum over all the wedge products of a given vector bundle. So again, this equation should be read order by order. This is called the quantum Winning relations of the equivariant quantum K-theory ring, which is proposed by these people in their paper. They proposed these relations based on physics reasonings, but later on they proved it in special cases such as the Grassmannians, the incidence varieties, and the complete flag varieties, and showed that these relations give rise to a complete set of relations and are exactly the relations of the quantum K theory. So in other cases, this is still conjectural. Finally, let me talk about the relationship between this integrable model and the double beta-Grothendieck polynomials. For this purpose, let's restrict ourselves to the complete flat variety case. That is this small n is equal to capital N, and the k sub n minus I is equal to I for every I. So first, from the explicit expression of the R matrix, we can compute the action of the B operators on a state, on this state exactly. Here, this Ni takes values from 0 to n minus 1. So it can be computed to be like this. It's a sum over a bunch of integers denoted by m1 through m minus 1. It looks quite complicated, but let me show you how it works by this diagram, so it'll be more clear. So in order for this state to be non-zero, the last side of the state has to take the zero state. The zero state corresponds to the first unit vector, and m1 must be k. And mi must be greater than or equal to ni. If mi is greater than ni, then ni is fixed. If mi is equal to ni, then ni is moved to the next site where mj is equal to nj. And the last site, the zero state on the last side is annihilated and replaced with the previous site, the previous ni, which equals to ni. And k jumps into the first side where ni is equal to mi. And similarly, we can compute the right action of the bk operator on the dual state. Still is given by a sum over a bunch of integers, and pictorially it is given by this. It's just that the direction of the arrows are reversed, and in the resulting state, the k state is annihilated, and the state the last site is in the state 0. Okay, from these explicit expressions, we can show by induction the following result. Here, pi is some permutation in Sn. And in this expression, the state indexed by some permutation is defined to be the state given by such that the I side is in the state Wi. Okay, so this lemma states that this sequence of B operators acting on Si pi plus beta pi is equal to this sequence of B operators acting on the state pi. The difference is very slight. It's just that the positions of Bi and Bi minus 1 are swapped. Although the variables the sigmas remain in their positions. And on the other hand, we have the following commutation relation. So in this commutation relation, this A, the subindex A is smaller than the subindex B, and if we swap BA and BB, then this swapping is compensated by the action of the beta divided difference operator, partial beta I plus beta. So it is amazing to see that this beta divided difference operator is encoded in this in the expression of the R matrix. And from these facts, it is easy to compute this this identity. So here, the sequence of B operators are the same on both sides. If the length of Si pi is greater than the length of pi, then the sequence acting on the state Si pi is equivalent to the sequence acting on pi, followed by the application of this beta divided difference operator. And the proof is easy. If we take the state Si pi plus beta pi and act on it by this sequence of beta B operators, we can switch the positions of Bi and Bi minus 1 and replace the state by just pi. This is guaranteed by lemma 1. Okay, and then we can switch them back, but then we need to insert this beta divided difference operator plus beta due to this commutation relation. Then because beta pi appears on both sides, we can drop it. Then the conclusion follows. Okay, with these lemmas, we can prove one of our main theorems. So consider the state on the left-hand side of this identity. This theorem states that if we expand the state in terms of the states indexed by these permutations, then the expansion coefficients are exactly the double Bethe-Grothendieck polynomials. Here, O minus Ti is minus Ti divided by 1 plus beta Ti, and omega n is the longest permutation in Sn. So we can see that this state generates the double Bethe-Grothendieck polynomials. So let me sketch the idea of the proof. So first, we take the state with the states 1 through n minus 1 in the strictly increasing order and place the zero state arbitrarily somewhere, and then act on it by this sequence of B operators. And as we can see, because Bn minus 1 kills the n minus 1 state, Bn minus 2 kills the n minus 2 state, and so on. So this state must be proportional to the pseudo vacuum, which is 0 everywhere. And this proportionality coefficient is just this double Bethe-Grothendieck polynomial, where this rho k is defined to be the product of k successive simple transpositions. So this identity holds. This means that this identity means that the theorem holds for omega n, W inverse is equal to rho k. And from here, we can prove by induction. Assume now we want to assume that we want to permute the states from 1 to n minus 1. So we can write omega n W inverse as pi times rho k, where pi is a permutation of n minus 1 elements. then we can use lemma 2 and the recursive definition of the double beta-Grothendieck polynomials to show this identity, the identity of the theorem holds by induction on the length of pi. Okay, so this is the expansion of this special state. But we want to relate the double beta-Grothendieck polynomials to our Bethe ansatz states. So to proceed further, we need the following definitions. So first, we define partial bar to be this partial plus beta, and if W is written as the product of transpositions, we can define the corresponding operators indexed by W to be the composition of the beta divided difference operator or partial bar operators of these corresponding to these transpositions. Okay, then we can show this lemma here. So again, if we want, we consider n minus b operators, and we randomly swap the order of the subindices, and we want to reorder them back. Then this procedure is this reordering is compensated for by a partial bar operator. And then we need this generalized Cauchy identity proved by Baker et al. They proved that this identity in the form of the first equation. Here, this G indexed by two permutations is called by axial beta-Grothendieck polynomial. If you're unfamiliar with the definition, it's okay. This identity can be equivalently written in the form of the second equation, which might look more familiar to you. So when beta is 0, this is just the Cauchy identity for the double sugar polynomials, and when beta is equal to -1, this is the Cauchy identity for the double beta-Grothendieck polynomials. Then from these, we can show the following lemma. So this identity on the left-hand side of this identity is almost the right-hand side of the Cauchy identity, but the difference is that instead of summing over Sn, we are summing over elements in Sn-1 here. And then we make the following identification. We identify the elementary symmetric polynomials in sigmas with the elementary symmetric polynomials in the x's. Without this identification, we cannot simplify the expression further. But with the help of this identification and the Cauchy formula, we can show that this summation is equal to a single double beta-Grothendieck polynomial with variables x and O minus t. Okay, then we can state another main theorem. So this concerns with our Bethe ansatz state. If the elementary symmetric polynomials in sigma i's, remember that we have a minus I sets of sigmas, which are indexed by the superindex. So if sigma super i's, the elementary symmetric polynomials in the sigma super i's are identified with the elementary symmetric polynomials in x1, x2, xn minus I for all I, then the best ansatz state can be written as follows. So the first line of this equation is just repeating the definition of the Bethe ansatz state. And if we make this identification, we can show that in the basis indexed by the permutations in Sn, the expansion coefficients are the double Bethe-Grothendieck polynomials with variables x's and O minus ti's. So what's the reason for making this identification? So remember that in order to relate the Bethe ansatz equations to the ring relations of quantum cohomology or the quantum K-theory, the sigma n minus I or 1 minus sigma n minus I have to be interpreted as the chain roots of Si. Therefore, this identification means that the Xi should be interpreted as the first chain class of Si mod Si minus 1 when beta is equal to 0. And 1 minus Xi should be interpreted as a K-theory class of Si mod Si minus 1 when beta is equal to minus 1. So these so this justifies this identification, and these variables x's do have geometric meaning. So let me sketch the idea of the proof. So we prove by induction on the number of sites because we are considering the case of complete flag variety. The number of sites is equal to the dimension of the local Hilbert space. So the GL2 system has 2 sides, GL3 system has 3 sides, etc. And the n equals 2 case can be proved by direct computation. And then assume the theorem holds for n equals m. Remember that we have this recursive structure of the Bethe ansatz state. This is just rewriting the original definition of the Bethe ansatz state, where the expansion coefficients psi are regarded as the coefficients of the Bethe ansatz state of the system in the next step. Okay, and from the inductive hypothesis, this coefficient psi and coefficient of psi and minus m is given by the double Bethe-Grothendieck polynomial, where this Wm is in Sm permutation. It's a permutation of m elements. Okay, from these, we can compute like this. So now we know that this is true for psi and minus m. Then we want to go one step further. We want to compute the coefficient of psi and minus m minus 1. So we take this inner product. From the equation, the first equation of this slide, we get the double Bethe-Grothendieck polynomial. The first double Bethe-Grothendieck polynomial in the bracket. This comes from the inner product. between this Vm and the psi n minus m. This is due to the inductive hypothesis, and this partial bar acting on the second double beta Grothendieck polynomial is from these B operators acting on the Bethe and this pseudo vacuum, because this is because of the lemma 3 and lemma 4. Because lemma 3 gives us this partial bar operator, and the lemma 4, the first equality is due to lemma 3. Yeah, because we have this permutation of the subindices, and it's compensated for by this partial bar operator due to lemma 3. Lemma 3 is here. If we swap the subindices, then if we put them back in order, this partial bar operator shows up. And then the second equality down here is due to lemma 4, because then we can combine these into a single. This lemma 4 allows us to combine this summation into a single double beta Grothendieck polynomial. Okay, so this is an idea of the proof. So finally, let me summarize and show some possible outlook. So the Bethe ansatz equations of this GLN asymmetric 5-vertex model give rise to the ring relations of the equivariant quantum cohomology when beta is equal to 0. And they give rise to the equivariant quantum K-theory ring when beta is equal to -1 of the flag varieties. And this state on the left-hand side has this expansion, which means that all the double beta Grothendieck polynomials can be generated this way. And even further, the expansion coefficients of the Bethe ansatz states are the double beta Grothendieck polynomials, with variables being the term classes of these line bundles, Si mod Si minus 1, and the equivariant parameters. Some potential future works include the following. So first, we have established a correspondence between this quantum integrable model and the quantum cohomology and the quantum K-theory of flag varieties, only at the level of ring relations. So it would be great to, as in Gorbunov and Korf, to give Frobenius algebraic structure to the Hilbert space and show that this algebra is isomorphic to the corresponding, is isomorphic to either quantum cohomology or quantum K-theory. We can also consider the Q deformation. The Q deformation for the R matrix is known. It was studied by Baker et al. They consider this 2D lattice model and showed that the partition functions are the double beta Q Grothendieck polynomials. So maybe we can also generalize by considering the Q deformation. And it would be also interesting to consider other types of boundary conditions and see if these other boundary conditions can give rise to some other algebraic structures. Okay, that's all for my talk. Thank you for your attention.
Okay, thank you for your talk. Questions?
Sorry, can you again explain me theorem 2 of your topic? When you expand eigenstate into basis.
Mm-hmm.
Yeah, I try to understand the statement. So it say that coefficients is the same Grothendieck double polynomials, but variables has other meaning. Yes.
Yes, yes.
So
Yeah,
in
they
terms
are.
of
I mean, these variables are different from the spectral parameters. So it's different from theorem 1 in that here the expansion coefficients are the double Beta-Grothendieck polynomials, but the variables are the spectral parameters in these B operators.
yeah,
But
and T, sorry, and T, it's a play a role of inhomogeneities from point of view of integrable model, yes?
well, the T, yeah, the TIs are the weights or the equivariant parameters of the model.
Here, X, it's in twist parameters, yes? Or what?
X no, X is not it's not part of the integrable model. The X's are not part of the integrable model. We just make this identification from geometric considerations because if we want to interpret the Bethe equations as the ring relations of the quantum cohomology or quantum K theory, then these sigmas are chain roots. And we can, other than the chain roots of the SIs, we can use the chain roots, the chain classes of the quotient bundles, SI mod SI minus 1. So it's a change of variable. You can say that it's a change of variable. With this change of variable, this Bethe state can be expanded with coefficients being the double Beta-Grothendieck polynomials.
But you obtain this access from Bethe equations. Or what?
I mean, the X's are defined to be that to make this identification work. The L's elementary symmetric polynomial in sigma I is equal to the L's elementary symmetric polynomial in x1 through xn minus I. So there are always n minus I variables for a fixed I.
Thank you.
You're welcome.
Okay, let us thank the speaker again.
Thank you.